In this unit, we're going to talk about file systems, volumes, encryption, partitions, and things like that, even quotas and so forth, and how that affects security for our operating system for Linux. So our topics will be the File System Hierarchy Standard, or FHS, file system mounting options. We'll talk about remote file systems like NFS and SAMBA, and then file system encryption, and finally, file system quotas. So what is the UNIX superstructure? Let's talk about Windows first, right? Most of us are familiar with Windows. Typically, you'll have a C drive, a D drive, right? Just to kind of draw, a parallel here. You go into the C drive on a Windows system, you have a Windows folder, which contains your operating system files and your drivers, your registry. You'll have your program files directory, which has all of the files that, are for programs, right? And inside users, you'll have different folders for each user, and then they'll have their own files, and then so forth. You'll have other drives maybe for data or, for other program files and so forth, right? I think a lot of folks are familiar with this kind of Windows file structure. It's pretty standardized, right? Microsoft owns Windows, and they have this very standardized structure for their file system, right? Linux is a lot different. You always start with the root, the / right? And within that, you've got a bunch of directories. For example, you might have a home directory, and inside that, you've got the users directories, right, that are inside home. And this is pretty typical for a Unix system. Pretty much all Unix and Linux systems look pretty much like what you see here, right, at a bare minimum. And I apologize for the mistake there on the end, the two op directories. The last one should be var. But that's basically what most systems will look like. So where does that come from? Well, it turns out that comes from who is the authority, right, on these file systems for Linux and Unix? Well, it turns out that there is none, right? Nobody owns Linux. Now, Unix is a little bit different, right? But nobody really owns Linux. Nobody owns BSD, which is arguably Unix. So who came up with all these standards? Well, they're kind of de facto, right? Although I would argue that most of them kind of have their DNA in Unix, right? We go farther back in time in that you call from that first slide from our first lecture, I talked about kind of the origins of Unix and Linux, and really kind of all this goes back to Multics and all that, right? So a lot of this really kind of came from somewhere, but they really kind of became de facto standards, and eventually somebody codified those de facto standards into kind of a real standard, which is the Linux File System Hierarchy Standard, right? You can go to that URL and you can read a little bit about it, but basically that standard enables software to predict the location of files and directories, right? So by having a standard, I can always predict that my log files will be in var, my binaries will be in bin, the essential binaries in sbin, and so forth, right? I kind of know my config file should go to etc and so forth. Users can also predict the location of files and directories because of that standard, right? I know as a system administrator that if I'm looking for files related to doing configurations, I know I can go into etc, right? And I'm typically going to find what I need in etc. Not always, but typically, right? Again, it's kind of a de facto standard, right? We do this by specifying principles for each area of the file system. We describe the minimum files and directories that are required for compliance to this standard, right? And we also enumerate exceptions to the principles that we laid out and specific cases where there might be conflict, right? Where different people put things in different places and how we resolve those conflicts. So who's going to use the standard? Well, like I said, system administrators, but also software suppliers, developers, people who make the operating systems and the distributions, right? They're going to make sure they follow this standard so that everybody's pretty standardized. And users, of course, right? Because so they know where they can find things, right? All these folks will follow these standards to try to, make sure everything's organized in a similar way. There's also POSIX. So you'll hear the term POSIX compliant operating system. When you hear that term, a lot of times they're talking about, one of the things they're talking about is that in POSIX, they describe this hierarchy, this file system hierarchy. And it's a little different than the link that's in for Linux, but some Linux distros are POSIX compliant. I would argue that a lot of them are. And to have POSIX compliance, there's a different file system hierarchy, which is very similar to the one that's described in 2.3 that you see in the link to become POSIX compliant. What that means, though, is that anyone who says they're POSIX compliant or complies with IEEE 1003.2-1992, right? If they comply with that standard, It means that you can be assured that if you're looking, if POSIX tells you that there should be a file or a directory somewhere, that you will find it there in a POSIX compliant system. So when I develop software for a POSIX compliant system, I know exactly where I can find things. So POSIX, it's pretty important, right? And you'll see that as a requirement for a lot of folks. They'll say it's, we require a POSIX compliant operating system to run some software or in our environment and so forth. All right, continue on the UNIX superstructure. Typically, you'll have a bunch of directories, right? So what do we find in those directories? In the bin, that's your essential binaries. Boot has your static bootloader files and your bootloader. In dev, you have your device files. Again, one of those cool things about Linux and the elegant simplicity of Unix is everything is a file, including devices. Your hard drive is a file. Your CD-ROM drive is a file. USB drive is a file. Everything is a file, right? You've got etc, which is where all your configuration files are. Lib is for shared libraries like DLLs and kernel modules. Media is a mount point for removable media. MNT is a mount point that you use temporarily if you just need a place to mount something, right? Instead of having to create a directory. Opt is for add-on application software packages. It's not commonly used. You're not going to find too much stuff in opt. SBIN is essential system binaries. So that'll be things like the su command, the sudo command, ipconfig or ifconfig, ping, and so forth, right? SRV is data for services provided by the system. TMP is temporary files. USR is the secondary hierarchy, not to be confused with home, right? Home is something different. I know a lot of folks confuse USR and home, but USR, to put it in plain English, USR is where you find the core kernel files, right? The binaries for the kernel are typically in USR. And then finally var, which is where you'll usually find log files. So that's where we put them typically in var. So as far as the organization of our file system, usually you have a mount point. That's a directory that effectively becomes a shortcut to an external device. Partitions are a way to segment a drive. So we start with the drive, we partition it into multiple partitions. A physical drive is partitioned. Each one of those partitions is a volume, and those volumes get formatted to become a file system, right? And that's essentially how we, the hierarchy of how this works, right? Now, the physical disk structure. So a physical disk can consist of several, it consists of basically several disks, right? The physical drive is a bunch of disks, right? And I'll show you this in a picture here in just a second. And each side of those disks has a head, right? That reads and writes from the various platters. And then there's tracks, which are kind of like a record. You have these concentric tracks, which have sectors. Each sector has 512 bytes. You could calculate the size of a disk if you know the number of sectors per track. You multiply that by 512, the number of tracks per side, and then the number of sides you have right on those platters, and you've got the size of your disk, right? It's that simple. So what does it look like physically? So you've got these platters, right? And in the middle, you've got a spindle, which, is basically how, they all spin on a spin. That's what's going to spin the platter, right? And then you've got your tracks, right? The concentric circles that are the tracks, kind of like tracks on a record, right? But if you divide those evenly in these little pie-shaped sections, those are going to be your sectors, which are 512 bytes per sector. And then you've got your boom, which has the heads on it, and you stack those up, right? So here I've got 6 sides. I've got 3 platters. So that's 6 sides altogether, 3 heads to read and write. They read and write on both sides of that platter. And if you see there's kind of that vertical, all those vertical sectors, when you put those together, that's your cylinder. It makes a lot of sense to have contiguous data, contiguous address data all to be in the same cylinder because they're all being read and write at the same time as the actuator kind of, moves those heads around. I don't have the actuator on my diagram here, but that's what holds all the booms together, right? It's an actuator that moves them back and forth over the platter. So that's roughly what the physical architecture looks like of a disk, basically. Unless, of course, it's a solid-state disk, which is going to be completely different, right? Solid-state disks are nothing like this. But I would say that, spinning disk is still pretty common, right? Although the prices are coming down on solid-state for sure, but we still see a lot of spinning disks. So let's talk about partitioning. So a single disk partition table has room for up to 4 partitions. Those are called primary partitions. All operating systems work like this. It doesn't matter whether it's Windows or Linux, right? All of them, you can have up to 4 primary partitions, and one of those partitions can be divided further into 16 extended partitions, giving you a grand total of 19 possible partitions on any physical drive, right? So a physical drive can have up to 19 partitions on it. And then you can have additional drives, right? Well, it turns out in Windows, I think your limit to the number of partitions you can mount in Windows is something like 19 or 20. But in Linux, I don't know that there is a limit. Maybe there is, but I've never hit that limit. In fact, I know I've gone over 20 on some systems. It's not common, but certainly I have. It used to be more common in the old days when file systems were limited in size, right? You can only have 2 terabytes on some file systems, although those limits are really, they don't really happen anymore with 64-bit and all that, right? But so how do we deal with those partitions? Well, each partition, when you can create a partition using the fdisk utility. So fdisk is how you create a partition. That works in Windows too, right? So there's an fdisk command in Windows. There's also an fdisk command for Linux, right, to create these partitions. In UNIX, each directory can be a partition. Doesn't have to be, but different directories could be. Swap always has to be its own partition, right? So at a minimum, you're always going to have swap, and you're always going to have root, which is another partition. Those are only 2 required partitions for a Linux system. Beyond that, you don't have to have any other partitions. You certainly could, though. For example, some people make boot a different partition. var could be a different partition. tmp, USR might be a different partition. Home could be a different partition. That's pretty common, right? So those could be mounted as different partitions. So you can have a different drive, for example, holding all the home directories. It could be in a different location. It could be, a RAID somewhere, or a SAN, or a NAS, or using an NFS mount, or what have you, right? So those can all be different partitions. Those partitions have to be formatted. What is formatting? Well, if you run this command, less-f, and then dev, and then whatever the device is that's your hard drive. In this example, it's HDA1. For you, it's probably going to be SDA1 or 2 on your Google Compute instance, or I think it might be something else. But in any event, if you run that command on your active hard drive, what you're going to see is just a whole bunch of data, right? Just ones and zeros. It's not going to make any sense. It's all just disorganized, right? So what's a file system do? Well, a file system is going to organize all that stuff, right? That's the job of the file system. It organizes everything. To create a file system, to organize everything, you always have to start by creating a file system. The mkfs command is how you do that. Pardon the typo here. It's mkfs, not mke2fs. My example is correct, right? mkfs. So for example, that command is going to create a partition using HDA1, using your hard drive. It creates a partition using the ext2 format, right? It formats it to that file system, the file system of ext2. Lots of different file systems available, right? But if you were to run that command, if you ran the dd command, which basically just outputs the raw data, but it has some extra, it's unlike less, it has some options here. So for example, the count gives you every 8 bits, right, which is a byte. So basically you get your bytes, and it's the first 1024 bytes, and that's going to tell you that it's ext2, right? If you run that, right? You can run that command, and it'll show you that it'll show you that it's formatted ext2. Not that you would typically need to do that, but just as an example. To make a swap partition, it's a different command. It's mkswap. And you can use swap on to use that swap, to enable that swap partition. Use swap off to turn it off. You can have different swap partitions and enable or disable whichever ones you want to use, for example. There are lots of different types of file, or different file systems, right? But they are divided mostly into 2 types. Those 2 types of journaling and non-journaling. So journaling file systems are going to keep track of transactions that have been applied to the file system, and they can check against that file system data, and they can keep track of changes that are going to be written, right? Journaling was first supported in ext3, which I think was back in the 90s, so it's been around for a long time. In fact, almost all modern systems, by default, they're going to use something like ext4, which is a journaling file system, or one of the many other ones, right? There are lots of different file systems that you could use. You can research them. Here's a whole bunch of them that are from your textbook. You'll notice in that list, NTFS is one of them, right? NTFS, which is Windows file system. FAT16 is also a Windows, a Microsoft file system. So you could basically, mount a Windows disk, right? You could certainly do that if you wanted to. So again, there's a whole bunch of other ones in that list. Windows has basically two file systems, right? NTFS, and I can't remember the new one that Windows. I'm not really a Windows person, but there's a newer one. I can't remember what it's called. And then of course there's FAT, but I don't even think they support FAT anymore as a mounted file system in Windows if it's not like a USB drive or something like that. But in Linux, there's a lot of them, right? This huge list of different file systems. All right, so let's talk about mounting. In Linux, root can span many disks and partitions. Unlike Windows where you have C and then that's all one partition, you can mount different partitions into root in Linux, right? So it's a little bit more flexible. So for example, if you're adding a CD or a USB, you would use the mount command to mount that somewhere in your file system, anywhere you want, right? You can put it anywhere. It doesn't have to be like Windows where it's a drive letter. You can mount it into a home directory if you wanted to, for example, and you're going to use the mount command to do that. So for example, if I was going to mount a CD-ROM, this is the command I would use to do that. ISO 9660 is the file system for CD-ROM. Here it's being mounted as read-only, and the device is HDB, right? And that's how I mount the CD-ROM drive. You can make a directory, for example, called Windows, and then mount a FAT32 file system, for example. It's on an old Windows hard drive, right, into that directory. So if you CD into Windows, you're basically going to see all the files on that mounted Windows, Microsoft Windows hard drive, right? MKDIR, you could create one called NT and mount the Windows NT hard drive, right? Which is the newer, NTFS rather, the newer file system for Windows. I shouldn't say newer. It came out in 1996 or something, or 94, I can't remember. So it's certainly been around for a long time. FSTab is a file in Etsy that you're going to use to make these mounts permanent. If you run the mount command, it only mounts it in your session at one time. If you use FSTab, it'll mount it every single time the system is rebooted, right? So if I'm logged in, I run the mount command, it mounts it. It's available for all users, right? So it doesn't just mount it for you, it mounts it for everyone, because that directory is, the mount point, so anybody who references that directory has access to that device. But if I turn the machine off, it reboots, it comes back online, that mount's no longer going to be there. FSTab is how we fix that and make sure that it's always there when we reboot a system. Let's just finally with file systems, I want to talk about links real quick. This is a concept I think a lot of folks miss in their kind of Linux 101, right? Is what's a link? And there's two types of links. There's soft links and hard links. Let me describe what they are. To really understand links, we got to understand something called an inode. So when you create a file, so take for example this file structure. I've got some directories, and inside that directory I've got a file called index.html, for example. When you create that file in the file system on disk, it gets an inode. An inode is like an address for that file. If you think about a library, right, a book, in the old days, I don't know if they still do this, well, my library does, but you have a Dewey Decimal number on every book, right? And if you're in the card catalog, to find a book, you find the card that references that book, and it tells you the Dewey Decimal number to go find the actual book, right? And then you go to the shelf and you find it by the Dewey Decimal number, right? That's kind of like an inode, right? It's an address, so you can go and find it on the shelf, that book. If you didn't have Dewey Decimal numbers in a library, how the heck would you find a book, right? You'd have to go through the whole library to find it. That would never work. So we have to have some kind of an address to go and find that book, some organization system, and that's what file systems really are. It's like a kind of like a system of organizing all the books that are on the shelves. Now here's the thing, if you think about a library, sometimes you can have a different card. You can have multiple cards that tell you to go find the same book. Maybe I've got one card for the author, another one for the subject, and another one for the title, right? 3 different cards, but they all point to the same Dewey Decimal number, to the same physical book. I can take those cards in the card catalog and I can remove one of them, but that book is still there on the shelf, and that's kind of like an inode. Even if I remove one of these files, doesn't matter which one, that inode is still there, so the other file is still valid. This is what's known as a hard link, right? A hard link references is when the file references an actual inode on disk, right? The actual address of that file on disk, the physical address, right, on the shelf for that particular file, right? Now, there's another thing I could do is I could create a file that's a soft link, right? A soft link is where rather than referencing an inode, it's its own inode, right? So it's its own file, its own inode, but the contents of that file is simply a redirect to where the file is that you're linking to. This is a soft link. What's important to know about hard link versus soft link is that a hard link typically only works in the same file system on the same partition. You cannot generally do hard links across different file systems. That would be like in a card catalog in the library, one of the cards referencing a book that's in a different library, right? It doesn't work. You can't do that, right? Because they might have their own system for storing books in that library. You can't just reference another book. But what you can do is have a card that says, we don't have that book in our library, but here is how to go get that book somewhere else. And that's like a soft link, where it's not the physical book, it's how to go and find that other book at a different library. Like go to this library and you can find it. So a soft link can traverse across partitions. Okay, so that's the difference. Now, could you use a soft link on the same partition? Absolutely. Nothing wrong with doing that. You can certainly do that. However, this is the problem with soft links. If you remove the file, the inode to which that soft link references, then that soft link becomes dead, right? It doesn't go anywhere. So now on the other hand, with hard links, once you remove the last file, then that link, all the links are gone, right? So it's a little more intuitive in that sense. But just so you know the difference between a hard link and a soft link, I just want you to know what they are. Almost every file system in Linux supports both hard links and soft links. Even obscure ones like we might try with our lab using Fuse to mount a Google Drive, for example, and even that supports links, and you'll be able to use that. But they don't typically support, for example, that one, they don't support hard links, right? Because there are no inodes in a Google Cloud bucket, right? The concept of an inode doesn't exist, so you can't do a hard link. But a soft link still works because that's just a file that references the relative location to another file, for example. So let's talk about network file systems. I talked about the physical file systems. A lot of times we use network file systems. The first one is NFS, or network file system, literally called network file system. It was developed by Solaris Sun Microsystems. I know we talked about Sun Microsystems previously in this course, right? We talked about the yellow pages, right? We talked about Network Information System, right? Or NIS, which is the other kind of the sister to NFS, right? Also developed by Sun Microsystems. So they developed a lot of stuff at Sun Microsystems, but it allows a server to share a selected local directory hierarchies with other systems, right? So it's file sharing, and there's a lot of reasons we do file sharing, right? It can support workstations that are diskless, dataless, and they're standardized, right? So you can have, workstations that aren't storing any data. All their data is really on a server somewhere, so nothing's physically being stored there, right? They're just clients, kind of like the old days with dumb terminals, right? A little bit like that. There are different versions of NFS. NFS versions 1 through 3 are no longer common. NSF4 supports low latency and low bandwidth connections. It uses a single port as opposed to dynamic ports. It has built-in security, so it has encryption. You can lock in. It has lock and mount built in. It can support stateful operations, improve performance using caching on the client. It supports ACLs, which we're going to talk about later in this lecture. I'll talk about what ACLs are, but it kind of is a step above discretionary access control that we talk about in the beginning of this course. So here's what it looks like, right? You've got a server and a client. So on the server, you've got a disk which has, maybe a couple different file systems. And then you've got this file system interface and then the NFS server. So a client can mount through the NFS client, they can mount to the NFS server and get access to that file system on the server. That's basically how it works, right? So if I'm a user on a client, I have a file system interface that has various file systems. One of those file systems I can mount and access is NFS, which really points to another location. And that could be transparent to the users. They don't even have to know that that exists, right? That it's NFS. To them, it might be transparent. They just know they're using files. They don't know that it's mounted with NFS in a different location. So the DF utility is how we show directory hierarchies with NFS. -H makes it human readable. So the host name indicates the file system is mounted through NFS. And -T adds the file system type. NFS security. So by default, NFS uses the auth-sys authentication mechanism, which uses the trusted host paradigm. What does that mean? That means that it's a trust based on IP addresses and host names. And that's not very secure, right? It uses the UID and GID of the user on both machines. Again, we talked about those in a previous unit. That's also not very secure. They could be spoofed, right? Just like IP addresses can be spoofed. If I assume an IP address that I know has access to a volume and I know a UID of a user, then, I got access to what I want, and there's really no other authentication really built in here, right? So again, they can be hacked, right? It's not very secure. So the point of all this is NSF has a lot of uses. I'm sorry, NFS, I spelled that wrong. NFS has a lot of uses, a lot of great reasons to use NFS on a network, but you generally only want to use it within a trusted LAN. You generally would not want to use this outside of a LAN. You're not going to want to use this, for public access or to mount over the internet directly, right? I guess you could with RPC-SEC. I'm not going to cover that in this course, but NFS really just uses RPC, just like, if you recall, we talked about NIS, that also used RPC, right? And there is a version of RPC that can be encrypted, so that's great, but I still wouldn't recommend it, NFS over a public internet, right? To mount that over the internet. So there are other mechanisms much better for that, like SFTP, right, that are kind of built for that sort of thing. So to install NFS, basically, you have to have a bunch of packages. You have to have NFS utils, RPC bind, and on Fedora or Red Hat, you have to have system config NFS or CentOS, which we're using in this course. So you make sure that RPC bind is set to run. It's going to use that, just like NIS when we talked about that. You would install the NFS package. It's NFSD, right, to install the package. Mount D, you also have to install an rQuOTA-D, right? Those are supporting packages for NFS. So to configure NFS, basically NFS v4 is going to use TCP wrappers to control access. So you have to edit etc host allow and host denial. This is a little bit different in CentOS. I actually wrote this slide for Fedora, but a couple years ago, but it's the same basic. We're not going to do this in the lab though. But once you do this, you can see a list of directories that are eligible for mounting an NFS, or you can put that list in the etc exports file, right? So in etc exports, you say, here's a folder, or a directory, I should say, this is Linux, that's eligible for use with NFS. It can be mounted with NFS. So somebody can go, so exports is basically on the server, you create a directory and say, okay, this directory, I'm going to allow people to access through NFS. And then a client can go and mount that through the server. They can connect to the server to mount that particular directory. That's basically it, right? So it's not too complicated, right? It's a relatively simple mechanism. NFS is currently, as of now in 2016 server and Windows, it is compatible with Windows. So this used to be our only option for sharing files with Linux was to Windows with Samba, but NFS now also works, which is kind of nice. So the NFS client is basically what you're going to use to mount a remote directory. So you have to install it. Again, same packages that are required, NFS utils and RPC bind, and then you can use the mount command to mount a remote directory, right? So you have various options. You can use the RO for read-only. No SUID runs the setuid programs with regular permissions. No dev prevents character and block devices, right? So you can't mount devices, right? And for frequently mounted directories, you would use fstab to make sure it automatically loads that NFS mount every single time you reboot, right? So if everyone's home directories, for example, is mounted through NFS, you would want to make sure it runs every time you reboot the system. So generally, I don't think I'd recommend using NFS for that, but you could. AUTOMOUNT is basically mounts NFS directories on demand. For example, a user's home directory, which is referenced in LDAP, right? So you can use LDAP, for example, when somebody logs in with LDAP, LDAP can reference AUTOMOUNT NSF directories to mount their directory in real time as they log in, right? So when you log in, it automatically mounts your home directory. You log out, it's not mounted anymore, right? It's mounted in your user space, as an example. And that's kind of similar to how Active Directory works, right? You log in on a Windows machine with Active Directory, and your home directory could be mounted from a file server. Now, the other option for file system, shared file systems, is SAMBA. And this is SAMBA basically is an open source implementation of SMB, or Server Message Block, I think it stands for, which is Microsoft's protocol for sharing printers and files, for both printers and files, right? It's part of the NetBIOS stack of protocols, I think, in Windows. But SAMBA is going to allow Linux systems to share files with Windows systems. Although, like I said earlier, NFS also kind of works with Windows now as well. So some of the components you need, it's a whole bunch of components. I'm not going to talk about all of these in this class, but your book certainly talks about this a little bit. They actually don't go through all these different components, but you would need all of this stuff installed. So when you install the SMB packages with your package manager, it's going to install a whole bunch of stuff that you need for SAMBA to work. And then you would install SAMBA with the SAMBA package, right? And once you install it, you'll be ready to configure it. Again, I'm not going to go through all these different components, but just understand you need all this stuff in order to use SAMBA. So to configure SAMBA, basically you're going to use a GUI-based tool to do that. That's the easy way to do it. There's also command line tools that you can use to configure SAMBA. SAMBA is not for the lighthearted. It can be very difficult to set up, but there is a web-based tool, right? Because a lot of times with Linux, you're not going to have a GUI, right? We don't have one in our labs. So you can use the web-based config tool. So you can go to a browser on a different machine and configure SAMBA on that machine. I do have to say that usually if I use SAMBA, there's some other packages that can implement SAMBA that make it a little bit easier to implement. So there's lots of other ways to do this, but the important takeaway in this class is that if you do need to share files between Linux and Windows, SAMBA is the way you have to do that. Again, just like NFS, this is not something you would do outside of a LAN. You want to make sure from a security perspective that that this is in a protected LAN, right? If you're going to use SAMBA. All right, let's talk about file encryption. There are two types of encryption when we talk about Linux. File encryption, right? There's also network encryption. We're going to talk about network encryption later on in the course. But in this unit, we're going to talk about file level encryption. And there's two, there's kernel space and user space. So in the kernel space, you have things like the secure hash algorithm. You've got AES, or the advanced encryption standard. You've got disk encryption subsystem. You have the enterprise cryptographic file system, or eCryptFS. And in the user space, you have GNU Privacy Guard, or GPG, which is the GPG command. We're going to try that in the lab, which with the -C switch, you can encrypt any file with a passphrase. And then you have the enterprise cryptographic file system, or eCryptFS, and then Linux unified key setup. So these are some of the user base. So in other words, user space is where users are setting up folders or directories where they're going to enable encryption. They'll have their own passphrase or their own key-based encryption. Whereas kernel space, the users don't get a choice. If they write a file out to a directory, it's always encrypted, right? In the Windows world, the equivalent would be something like BitLocker, right? Something like that. So encrypted files, there's really two methods to encrypt the files. You have passphrase or public key. I'm going to talk more about how public key works later in this course. For right now, we're going to try this with passphrase encryption because it's the easy way. Passphrase is where you have one password to both encrypt the file and unencrypt the file. With public key, you have a private key and a public key, and you have to exchange any, you encrypt the file with a public key, and then you can only unencrypt it with the private key, right? And the idea is that you can share your public key with anybody, so anybody can encrypt the file for you, but only you can unencrypt it with your private key. I'll talk more about that in a little bit more detail later in the course when we talk about network encryption. That's where really this private public key becomes a lot more important. You can encrypt entire directories with eCryptFS. You can also encrypt directories with loopback encrypted file systems, which are based on PAM. We learned about PAM previously, right? You have eCryptFS, which includes both user and kernel components. And you can also use the user account, the user's password rather, can be used as the passphrase, right? So that way a user, their password is basically their passphrase to unencrypt files in their, if they do encryption, right? So again, various ways we can implement encryption. We're going to try one of these in the lab just to kind of play with it. So an encrypted volume, you can also encrypt an entire volume, right, or a partition. So you would run these, the first command, really the DD command, basically all you're doing there is you're writing a bunch of random characters to the volume that you want to encrypt. And then you're going to use the crypt setup command to actually format a volume with encryption. And then that's it, right? You've got an encrypted volume. There's a little bit more to it than this, but I'm not really going to cover in this course how to create an encrypted disk. We're not going to do that in the lab in this unit. We might do that later on in a different lab. We might come back to this. So second to last topic is quotas. So quotas basically, so once a directory or a partition becomes completely full, that can cause a lot of problems, right? Why would a directory become full? Why would the file system become full? Well, it could be a whole bunch of log files getting written out. It could be people just archiving all of their data. Some people just don't like to throw away files, right? So they just keep putting more and more files in there. Processes can stop working and the operating system can become unavailable if, once a file system is full. So this is not a good thing. So we can enable quotas to prevent people from using the entire disk. It's going to prevent a lot of problems if we enable quotas. They can help limit the damage also if a user account becomes compromised, right? Because they're not going to be able to use the entire disk, right? It's going to limit what they can do. So quotas are generally on shared systems. You're going to use quotas. I would say that for Linux as a server, which is more common, in today's world, we don't really have a lot of Linux systems where users are accessing them to do stuff, right? Although that is, databases and things like that. But I think for the most part, quotas can also be very useful to make sure that that we don't have log files that are going to take over the entire system, things like that. So configuring a quota, the first step is you're going to use the fstab command to enable the quotas. Then you're going to remount the home directories so that everybody, basically it's going to basically take effect having all these quotas. And then you can use the quota check command to see, basically to take a look at, initialize that database and then make changes to quotas essentially. And again, I'm not going to actually do quotas in the lab this week. I think I've been giving a lot of labs in this class, so I'm going to kind of dial it back this week. But those are some examples from your textbook. And finally, let's talk about access control lists. We know discretionary access control is the default in Linux, but you can also use ACLs to manage access to files. So it allows you to set different permissions for specific users and groups, whereas discretionary access, you can only have one owner of the file, one group that owns the file, and then you can set permissions for everyone else on that file, either for people that are in your group or for for everyone else. But it doesn't really give you a lot of control for those files, right? So ACLs give you much more granular control of the files in your file system. And it kind of gives you a secondary level of discretionary access control. ACL support in Linux has been around for a long time. It supports NFS as well, right? So we can use it with NFS. So it's pretty handy to use ACL to apply more granular permissions on a Linux system than what's available with the basic discretionary access control that comes baked into Linux. So to configure for ACLs, it's similar to configuring your file system for quotas. There's two standard ACL commands, get FACL and set FACL. To implement ACL permanently, you would configure it on an appropriate file system in etc tab in the config file. So every time you turn on the machine, the ACLs are applied. File systems that require custom access are good candidates for ACLs. Home directory, right, is also a really good candidate for ACLs because sometimes you want more granular control on how people access those home directories. I would say on multi-use Unix systems, ACLs are kind of a must. But for server-based Linux systems, we don't generally have to use ACLs because, we're providing services with Linux. And I would hazard to guess that the vast majority of Linux systems out there are probably servers that are serving something like a database or a file system server or a DNS server or a mail server and so forth, right? Which we don't really need ACLs for a lot of those. So to configure, again, it's just going to be a couple of steps. You're going to use this command to set ACL permissions for a specific user by using their username or their UID. You can set permissions to a specified group, again, by using their group ID number. This is the from the password file, right? The PASSWD file in Etsy. And then you can set standard effective rights masked for ACL permissions for users and groups for when they create a file, for example. And then, of course, you can do much more granular control on a per file and per user basis or per group basis. So finally, best practices. So first, we talked about the hierarchical file system and understanding that file system hierarchy, right? It's good to understand that. That certainly helps us understand our systems. Make sure we pick the right file system formats. Make sure we use journaling file systems in case we need to recover from problems. You know, if a system suddenly turns off or something and we don't want it to get corrupt, journaling file systems generally are less likely to be corrupt. Although I would argue that, you know, in the beginning, journaling actually sometimes would make file systems corrupt a little easier, but today that's not the case. And you know, a lot of these newer, mature file systems, corruption is much less likely than it used to be in the old days, which is nice. So some other best practices: the local file and folder permissions provide different levels of discretionary access control. File and folder permissions can be different when you share it over a network, so it's important to understand that just because you set the file permissions at the local level, if it's shared with something like NFS or Samba, those file permissions don't necessarily follow over the network, right? So it's really important to understand that. But we can use things like ACLs in conjunction with NFS to make sure that works. We can use quotas to limit damage in case of data exposure, limit the amount of space or the number of inodes that a user can take up, right? We learned about inodes with our links, right? Users and group can be reviewed regularly with their quota reports and see, you know, if anybody's getting close to using up all their space. And of course, ACLs we can get a little bit more granular control over access control with ACLs. All right, so that's basically the content for this unit. I have kind of an appendix. If you don't need, I'm going to do a review of what many of you would have learned in a previous course. You don't necessarily have to watch the rest of this video, but in case you need kind of a refresher, I'm going to continue on in this video with some additional information about how to navigate in the file system. So let me talk about how to work with directories and so forth. So for example, if you want to find out what directory you're in, you're going to use the pwd command and it'll tell you what directory you're in. In my case, I'm in home student. I can change directory to, say, the documents folder, and then I can change directory to old docs, right? Which moves me down in that hierarchy to a different folder. If you use cd ... it'll take you back up, right? So if I do cd ... it's going to take me back up into documents, and I can use the pwd command to see where I am. Continuing on this theme, so there are different types of files on most Linux systems. You can have text files, binary data files, files that are executable program files. They have, you know, machine code that can be executed. You can have files that are actually directories. You can have links like hard links and soft links, which I talked about in this deck. You can have special device files, right, like your HDA1 or SDA1 or 2 and so forth, or USB and CD-ROM drives. And then named pipes and sockets, which are also technically files, right? So you can literally write to the network through a file, for example. That's what a socket is. File names generally follow conventions. In Linux, file names can be up to 255 characters. You have to avoid using shell meta characters. It can contain alphanumerics, right? So you can't use the grave symbol, for example, on a file name, right? Because that's a meta character used for shell commands. But generally, the extensions are not required, right? They really don't mean anything in Linux. The extensions are completely meaningless to the operating system and the file system, unlike Windows, where extensions are kind of used by the operating system. But in Linux, they're completely meaningless. They're really there for us as a reference, right? It's just convention, right? Typically, if you have a C source code file, you'll call it .c. If it's a C++ file, it's .cc or .c++ or CPP if it's a source file. If it's a web page, .html. If it's a text file, it's txt. If it's a tar, you use .tar, right? Which is you hopefully you learned about that in your previous class, how to tar files, right? How to compress files. Well, tar is not really compression, right? It's really an archive. But image that's a JPEG should be .jpg. But again, these are not set in stone. There's no reason, if you have a file that happens to be an image, you don't have to call it something.jpg. You could just call it something, or you can even use a different extension. You could take a JPEG and call it a GIF, or take a bitmap and call it a TIFF. It doesn't matter, right? Generally, though, it's not best practice to do that. But important to understand that none of that really matters. Linux actually deals with files by looking at their headers to figure out what type of files they are. It doesn't even care what the extension is. It's not really used. So files and directories. So if you want to look at a list of your directories, you'll use the ls, or all of the files in a directory. You use the ls command. So for example, ls-f will show you which ones are, it'll only show you directories, or files rather, versus directories. ls-l shows you everything, but with some additional information, right? So this is like the detail view in Windows, for example. Here you can see whether something is a directory, which is the letter D is for directory. An I is a symbolic link. B and C are usually device files. If it's an N, it's a named pipe. It's F is if it's a socket. And all other files are just going to be a dot, or a dash rather, right? So if it's a dash, it's just a file. But if in place of that dash you see a D, an I, a B, a C, an N, or an S, it's one of these other different types of files, which are special types of files. So for example, if I type file yp.conf, it's going to tell me, the file command is going to tell me that it's a ASCII English text file, right? By looking at the header. If I use file star.conf, it's going to tell me what type of file all of my different configuration files are, right? So is it a binary file? Is it UTF-8? Is it ASCII, right? So how is that file encoded? That's what the file command is going to tell me. If you want to look at the contents of a file, use the cat command and it'll output the contents of a file. If you want to see the contents of a file another way, you can use the head command. For example, here if I type head-n5, it's going to show me the first 5 lines of a file. And likewise, if you use the tail command, it's the last 5 lines of a file. And the more command or less commands allow you to see the file in chunks so you can kind of page through the entire file. Binary files are basically files that they don't contain text, right? It's binary or machine code sometimes. They don't have to be machine code. Sometimes they're just binary like config files and so forth. They're not files necessarily that you would typically edit, right? Bin files are usually edited by applications and programs, or they're actually applications and programs or executable files. You can view those contents using the strings command. It'll output the actual binary data. You can also use the OD command to output binary files. It'll show you the file either as decimal, right? So it'll show you the decimal represented by each octet within that file. Octets are groups of 8 bits or a byte, right? So what is the what is the decimal equivalent of each octet or byte in the file? And then CD-X shows you the hexadecimal equivalent of each byte within a file.